with latest, what is it, most recent higher element and partitions and subset sums, and I think that's a very bad idea given that your exam tomorrow will be focused on graphs. You may get a problem earlier from quicksort, for example, but you'll get the papers tomorrow. I apologize again for being so late with those midterms. That's absolutely my fault. And we got overwhelmed with so many things. So if you're coming tonight, Ankur?
Yeah.
So if you be there around 6,
Yeah.
you should deal with the midterm grades and all other questions you guys have. And I need one of you to come tomorrow
Okay.
for half an hour.
Okay.
Either you or Amul. You have to bring those midterms with you. Okay? So here's a quick logistics. Trace. You guys fill in those trace evaluations? Hands up. Okay, thank you very much. If you didn't, please do so. Be honest and be constructive. Grades. People can check their grades. So far, I think we're grading what? Homework 10 now? 11?
10.
10? So things will get graded. I told them they take their time because they have exams and other things, but they will get graded. Please check your grades, make sure we have the right grades. If you don't know why, some people already asked some questions. Where are my grades? Some of them are not graded, but if they're graded, then and you don't have the grade you think you should, then we should check that out. Exam. Tomorrow. What is it, 10 a.m.? WVH. Is it 108 or 110? I forgot. There's one room in the down on the first floor of the computer science, WVH. So we'll update the website. This is a regular exam. Okay? So it will be the kind of exam people typically have in algorithms, not a knockout like the midterm was. You shouldn't feel too bad about the midterm because that midterm can fail a lot of Google engineers. So if you do, you don't score 280 points on it, that's not necessarily a bad thing. By the way, I don't know if this person is in here. I'm sorry, I know you very well by now by faces, but not by names. The midterm will be graded out of 200 points. I want to point out one name. Day. Sibendu? Day? Is he here?
No, he's not here.
Not here. Okay, so I know by faces. At least one or two people managed to score more than 200, so that means they're going to have 100% as the midterm goes because it's graded out of 200. A lot of people score about 130 or so, 140. That's about 60, 70% out of 200. So midterms graded or will be scored out of 200 total. This will be 40% of the grade. This is 40% of the grade. And the homeworks will be 20% of the grade. Because the midterms were so late, again, that's my fault. We'll have Sunday, Monday, and Tuesday. That's 4/22 to 25th office hours. To answer your questions. I'm sure there will be a lot of questions. What are my points? No, my algorithm works. Me saying, no, it doesn't. Here's a counterexample. That happens every single year. And I'm happy to go with you over all those problems until we make everybody happy or we drop dead. Because it's previous years I stay until 3 a.m. at night with students arguing about their midterms and finals. So we'll make sure to have that time. I would appreciate to do it to deal with the midterms if we can by the 25th, so then we can worry about the finals. And I think that's it in terms of logistics. Today, one more thing. Today, we deal with NP complete problems. And last time, what was it, RSA? Not for final. So if those two topics, as far as preparation for the final, you can ignore those, okay? But everything up to RSA, like linear programming, for example, that could show up in the final. All right. So what we're going to talk about today is a very important complexity issue, which is, again, that's not for the final, NP complete problems, or NP hard problems. What we want to get at is some problems are too hard to solve with computer science. So we've been going on and on about efficient versus inefficient things, and we say exponential problems are too hard in general, because if the input scales from, say, 10 to 100, then the solution will scale to 2 to the 100 complexity. It usually goes too high, too fast. Right? But we didn't talk about the nature of these problems yet. Now, those are very important problems in theory. A lot of the theory, both computer science and some chunk of mathematics, are based on these ideas. But they're also very important in practice. If you, every once in a while, you can encounter such a problem in practice. As in, you want to find a maximal subset of something. I'll give you some examples, of course. You should recognize that this might be a hard problem and check to see if it's a hard problem. I do not expect you as a master level to remember all those hard problems and be able to immediately, when you see such a problem in practice, to say, okay, is it too hard? But you should at least have a warning, hey, I remember Virgil saying something about those kind of problems. Maybe this, the one that I'm seeing today, it's one of these hard ones. If it's hard, perhaps you need to do some studying, some research, talk to other people. If you figure out it's hard, you shouldn't try to find a dynamic programming or greedy algorithm or anything like that. You should realize it's hard. Perhaps tell your boss, hey, what you asked me to do, it's not doable at scale. And then figure out, okay, how do we go? Since we cannot solve that problem properly, what do we do about it? So that's the other thing, what to do about it. So the one problem that we've seen that looks like that, is the knapsack problem. This green knapsack. Right. So we have a set of items with weights and values. And we want to maximize the set, the subset, set of items. We want a subset of these items maximize the values. So we want the S maximize the values subject to constraint sum of the weights is smaller than something. That was the typical knapsack problem. We want the maximum set of values that the weights don't break the knapsack. These kind of problems have an inherent hardness in them because We managed to solve the knapsack somehow, but we did make an argument that that's not really a polynomial solution in the input. So one concept we need, what do we mean by hard? Typically in English, solution is not of a polynomial of input size. That's what we typically mean hard, when solution doesn't scale polynomially in the input. So if something is of n cubed, where n is the input size, that's polynomial because n cubed is a polynomial. But some problems are not polynomial in the input size, the solutions we know. And this was such a problem. If you remember our solution for this problem, the runtime was what? Something to do with the input set size, how many elements are there, times
Capacity,
what?
knapsack capacity.
Z, right? And we say, naively means this may look like a polynomial in both inputs. I don't have a problem with the product. Product is, if I have two inputs n and m, or a and b, this is a times b, that's still polynomial, it's quadratic. Why is this not polynomial?
That is just one number.
This is really n things, but this is not really z. Z is a number, and the input, when I give z as an input, how many bits or how many things I'm using to write down z? Z is 100 versus 1,000 versus 100,000. How much is the input that I represent z on? Log z. So the actual input is size of I times log of z. So now the solution, you see, it's not polynomial in z, it's exponential in z, in the input. It's polynomial in z, but z is not really the input. Z is a number. I don't need, if the number is 100, I don't need 100 bits to write that number. But this is okay, because in this case, for reasonable sized knapsacks, z won't be that big, right? I mean, a knapsack will have a z of 1,000 or 10,000. Even then, that's okay. So while theoretically this is not a polynomial solution, it's still a practical, because we don't expect the size of the knapsack. The input might be very small itself, but we don't expect knapsacks to start having, like hundreds of billions this z, right? For most problems, I think when knapsack really comes down to an implementation, we don't expect z to scale that much. But this, so I don't want to talk about, again, of knapsack, but I want to talk about what's the inherent hardness in these problems. They are looking for a subset without enough structure. So the problem says, find a subset that does something. So in more general, hard problem. Find subset S included in the input. Input is houses or objects or something, right? That maximizes some criteria, say maximum sum objects, I don't know, but doesn't have not enough structure in the problem for efficient search. What I mean by this, by a structure in the problem, let's look back at the activities problem. Activities is still a set of activities that's being given, right? So I'm talking about the set of input of activities now. What is the problem asking? Find. Remember the activities problem that we did greedy? Not a fancy one from the midterm. That's going to be another back and forth with those activities, I think, when you guys see the papers. But it's just a simple one. What is that problem asking? It asks for a subset of these activities, right? Find me a set of activities that has the maximum size and they do not overlap. Right? I was supposed to schedule all these activities in a classroom, for example, and I can't schedule 2 activities that overlap. Why is that problem easy? That activity is problem. It still asks for a subset of a given input, right? But why is it not a hard problem? We can solve it with greedy linear time. Why is that?
We have to start and end times.
There is a structure of these activities in the input that allows for a very efficient search. What's the structure? What is given for these activities allows for a very fast search. The start and finishing time, which are fixed in stone, right? They don't change. They're not dynamic. They just give them to me. That start and finish time allows me to search very quickly for the maximum set activities that I want to produce. Again, I don't want to go back to that greedy solution. Just saying, in some problems, we have enough structure in the input, like those activities start and finish time. And we have a criteria, of course, maximum number of activities that can be scheduled. But the structure is powerful enough to allow me to do a fast search. In most problems, however, the structure that I have is very loose. Like, for example, those weights and values in the knapsack. That's not a good enough structure to allow me to do an efficient search in that space. So I'm ending up with an exponential search. Now, without the structure, it's easy to see why I need an exponential time solution. Why is that? If I don't have enough structure, why is likely the solution to be exponential? I'm looking for a subset in the input. So if I don't have enough structure, what am I going to end up doing? Try all subsets, evaluate the criteria, and output the one that's the best at that criteria, right? But if I try all subsets, or almost all subsets, some of them may be excluded because I can exclude them. How many subsets are there? 2 to the n, right? 2 to the whatever this guy has n, there's going to be 2 to the n. So the hardness of these problems is I'm asking you for a subset that has a maximal or minimal or some property, but I don't give you enough structure to look for that. So then you end up trying almost all subsets, evaluate all of them, and decide, okay, this is the best one. But that, by nature, will be an exponential time solution because the number of subsets is exponential. Everybody on the same page with me here? That is the nature of hard problems. And we usually call them brute force because if you check a lot of those subsets, even if you don't check all of them, but you check at least half of them, you end up effectively ignoring the structure, try all possibilities, and decide which is the best possibility, right? That's essentially a brute force solution. It turns out there's a gap in these problems. We don't know how to characterize these problems, middle ground. We know the problems that have enough structures like the activities. And for those problems, we can find a greedy solution or a pretty quick solution. That's clear and has been clear for 50 years now. We know the problems that are very hard, that they clearly don't have enough structure, that cannot be done. But in the middle, we, computer scientists and mathematicians, are very puzzled. Like, is there some problems that have a structure that's not trivial, but enough to make it not so hard? The problems that have no structure at all in the search space, obviously they're going to be exponential. If I don't give you any structure, you're going to have to try all of them, right? The problems that have an obvious structure like these activities, we know how to solve them quickly. But in the middle, we don't know, for some problems, is there some structure that may be possible to make them solvable, but we don't know how to solve them, and we contemplate we don't know how to solve them after so many years because we don't have enough structure, but we can't prove that. So this is a massive, massive open question in mathematics and computer science. For these middle ground problems that I'm going to show you, which way they fall in terms of this structure? Are they reasonably structured so we can solve them? Or are they not structured, so then effectively we do some brute force solution that's the only thing we know how to do? This is an open question. If you solve such a question, it will make you instantly famous and instantly rich. You'd also break the encryption to all banks on that occasion. Okay. So encryption, like we talked last time, it's one of these problems that we don't think it's solvable fast. Of course, it's solvable by brute force, but we know that brute force will take a long time. If somebody wants to break an encryption by brute force, it will take 200 years with all the computers in the world. So we're not worried about that. But we're not sure that for encryption problem, which comes down to factorization, we're not sure that maybe there is a structure that solves this problem quickly. We just don't know it. Very famous problem. A lot of smart people working on it. A lot of smart people miss their careers because they thought they're going to solve this problem. They banked their career on this problem. They failed. So they got fired because they didn't publish anything else. Right? So this is a problem that attracted a lot of PhD and researchers all over the world. So now I want to introduce you guys a little bit to what are those problems and why we think they're so hard. And then a little bit, if we have time at the end, how we might try to solve them, but not exact. Since we believe exact solutions are hard, again, believe, we are not sure, really. We believe, as in most smart people today in the world, believe the problems I'm going to show you don't have enough structure to be solved efficiently. So since that's our belief, we still have the practical issue. If you see such a problem in practice, what do? Well, you can give up, or you can try to approximate it somehow to say, I can't give you the best solution. Best meaning, for example, maximum set of activities, maximum set of items that maximize the value. Maybe I can't give you the best one, but I'll give you a good one. If you are a thief and you can't solve knapsack quickly when you go to the museum, well, you solve an approximative knapsack and you still get enough paintings, right, that value a lot, but maybe not the best possible set. Okay? So that's what we want to do. I'm going to use some slides because there are drawings here, and because I'm going to move fast to some things. Usually this is a 3 hours lecture, but I'm going to compress it into 1 hour and a half. There are some things that are critically important here. Again, the things that are critically important is what I just said. There are some problems. Typically, they're asking for a subset of the input. And as soon as somebody asks you for a subset of the input, whether they're objects in a museum or activities or numbers, I give you a set of numbers, subset sum, figure out if some subset of those numbers sum to the half of the sum. Midterm problem, right? That's essentially asking you for a subset of the items with a certain property. It's one of these problems. As soon as somebody asks you for a subset of the input and the number of possibilities are all possible subsets, I'm not just asking for subsets of size 3. That's easy because I can just go through all the subsets of size 3 and figure that out. But subsets in general, it's hard because there are many. You should immediately think, hey, do I have enough structure here to process those sets in a particular way that makes it easy, like with the activities, or not? And you should really take the time to think about that if you have it as a problem in practice, because if you try to solve one of these problems by brute force or by some algorithm, either you're going to fail or your program will never terminate. Nobody will try to do this. Again, quantum computing might be a solution here if it comes out alive. Currently, it's not that alive, so we cannot tell what quantum computing is going to do until it does something. Okay. So we're talking about these difficult problems. And again, the nature of this difficulty is this subset idea. So here's one that I want to point out, which I think we mentioned before. It's a very basic, very basic logic problem. It's called the 3-SAT. The book calls it 3-CNF satisfiability problem. Extremely simple problem. I have a bunch of conjunctions of 3 literals each. So this is A, or, you guys know this sign, or B, or this is not C, right? And there is an AND logically between them. That AND says you have to satisfy all of them. So you have to make this one true, this one true, this one true, this one true, this one true. Now, you can assign every literal for value true or false, right? Those are Boolean variables. And of course, if B is true, non-B must be false. If B is false, non-B must be true. You can't say B is true and not B is also true, because that's impossible. So the question is very simple. I give you a bunch of these conjunctions, if you want, right? Each of them 3 literals. Can you find some literals to make them one true, and the other literals to make them false, such that every single conjunction is true? Right? I didn't put the and between them because I want all of them to be true. That's why people put the and between. Now, to make one of them true, what do I need? One of them has to be true, right? Because this is or, inside each conjunction it's or. So if one of D or C or B is true, I'm done with this one. In here, I need either E to be true, or C to be true, or D to be false. Right? Everybody understands this problem, satisfiability? Can you set some chunk of these literals to true and the other chunk to false, such that all these conjunctions become true? Am I asking for a subset here? Is this one of these problems that says, here's a bunch of items, I want a subset of them? Is that what I'm asking or not? What are the items?
Values, possible values.
The literals, the logical variables. What is the subset I'm asking for?
Their values, 1, 0, the possibilities.
Exactly, in English, what subset I'm asking for?
Some sort of true variable.
Which ones are
Positive.
true? Okay. I'm asking a subset. The question in this problem is like before for knapsack and activities. Is there enough structure here to do this efficiently? Do we have a way to go by those literals like we did with activities, right? Activities, simple problem, greedy solution. Do we have such a structural way to go here, assign the variables to get it true? Now, it may not be possible to make it true. No matter what you do, it's going to be false. So then you have to output, it's not possible, it's false, right? Now, this is a very classic hard problem. It's like the most simple and hard problem. It turns out we don't know how to solve this other than trying all possibilities, right? If I try all possibilities, I pick all the subsets, I make them true, I check. Checking if a subset verified this is very easy, right? If somebody says, here are the subset of true variables, A, C, and D, therefore the other ones would be false. Is it easy to check the solution? It's very easy. I go through every single one of these. As soon as I see a true one, good, good, good. If I see false, 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 what do I say? No good, that failed solution. I can stop, I don't need to check the rest. As soon as one of them has false, 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 it's false, so I can just say that solution is no good. So checking an assignment or a possible solution, somebody who says, he comes down and say, here's your true variables and the other ones are false. Very easy to go through this formula, check all of them and check all conjunctions and say, if all of them are true, that's a good solution. If they're not, that's not a good solution. Notice here that the solution may not be unique. There might be multiple assignments that make this stuff true. Who's with me so far? Good. Now this, we don't know why it doesn't have enough structure. So far we know that we don't know how to solve this problem. But we don't know how to prove mathematically that there is no way, polynomial way to solve this problem. Effectively, we're saying every solution that's correct, that gives me exactly the answer, the subset that has to be true, or not possible when it's not possible, any such algorithm, it's effectively brute force. It will have to try a lot of subsets. Maybe not all, but enough of them to make it exponential in nature. That's what we believe, but we don't have a mathematical proof for this. It's a very fundamental question in theory, in mathematics, and computer science. Can you prove that there is no structural way to solve this problem faster than brute force? That's what most people believe today. All good mathematicians and computer scientists, without exception, believe there is no way to solve this problem with traditional computers, aka Turing machines. Our computers follow the computation model designed by Alan Turing. If you've seen that movie Enigma, did you? Okay. Alan Turing, very famous guy. He worked on cryptography. He had enormous impact into world history because his machine, that he was more of a theoretician, there's other people, engineers, who actually work on that machine, but he's the one who figured out the principle how it works. Together with the British and American intelligence services who intercepted German and Japanese messages, military messages, they managed to actually build a machine to decrypt those messages. See, the Germans and the Japanese didn't have RSA. So they work by heuristics. I'm not kidding, seriously. They have a heuristic. Heuristics in encryption were valid since like Julius Caesar. Like long time ago, people have thought to encrypt messages, especially military or state messages. They sometimes use reference from a book. A message will be the page number and the word number, and you get 17, 3, 25, 18, so on and so forth. If you have the book, you could decrypt that message. But if you don't have the book, it was quite hard. All these encryption schemas are easy to break because once you have a few messages and a few books, you could tell immediately if that book is the one being used, right? You can read just a little bit of that encryption in the book and say that makes no sense, it's garbage. That's not the book. Now, if they consistently use the same book, there are not that many books that back then, right? So how many books, like they're gonna use something very famous like the Bible. I mean, there was no Bible in Julius Caesar, but if people use a famous book and they start sending hundreds of messages, it will check quite easily to figure out what book is the one that makes sense all the time. Anyway, so Enigma was certainly much more complicated. It has billions and trillions of possibilities, but it still had this flavor that the signature of the message was always the same. And by just looking at things like that, you could figure out mechanisms to break it. Now, the actual breaking of Enigma, the Enigma machine was something like that big, like a typewriter. The breaking of Enigma machine, if you've seen that, since they didn't have computers, was a few floors full of lamps instead of transistors. There are no transistors like that, right? So he managed to do that, Alan Turing, and because they break military messages, British and Americans had a very unfair advantage to Japanese and the Germans, including sinking aircraft carriers in the middle of Pacific that had to do with decrypting those messages. Anyway, so then he further continued his research and developed this philosophical model of what computers can do and what they cannot do. These are called Turing machines. That's what all computers today follow as a model, including phones, including tablets, all of that. That's not quantum computing. Quantum computing is a different model. If that works, that would be different than this. So now, I can't explain why this is so hard other than I don't think there's enough structure to solve it. So of course, everybody here can see if I try all subsets, I'm going to find the one that works if one works. But trying all subsets, it's exponential into how many literals I have, right? If I have n of these variables, it would be 2 to the n subsets to try. How about 2SAT? 2SAT is the same exact problem, right? They're conjunctions, right? All of them have to be satisfied. See this end in between them? That means you have to satisfy these and these and these and these. They're 2 literals each instead of 3. They also Boolean. And the problem is, can you find a subset of these variables that satisfies this problem, or print not possible if there's no such subset? Do we have a structure in 2SAT to solve this problem efficiently? Right? The number of subsets is the same as in the other problem. Just the clauses here are 2 instead of 3 literals. But the number of subsets to try to make true versus the complement the remaining ones to make them false, that's the same problem. If I have n literals, I will have 2 to the n subsets to try. This is an easy problem. This is like the activities. Very easy to solve. By the way, this problem was one in the finals 3 years ago. Solve the 2SAT problem. 2SAT, it's very easy solvable. And here's the idea. You pick the first literal and you say, try some value for it. For example, try to make it true, right? If I make this true, what's going to happen with all the clauses that contain A? They're done, right? If I don't have a non-A, I don't have to worry about it. I make A true and A is gone from here and there is no non-A. The problem is if I have non-A, the moment I say A true, non-A will have to be false. And now to satisfy this clause, C must be true. So you can easily see that I can create an inference here, try A equal true, mark the ones that are satisfied, mark the ones that have non-A. If something has non-A, C must be true. And I keep going with this inference. Now I have C true, and maybe there's another non-A, I'll have a D that must be true, or some G. And then because C is true, again, all the clauses that have C are done. But the ones that have non-C must have the other one mandatory true. So, there's a very linear inference here that goes, assuming A is true, I can do some sort of linear inference. In linear time, I can decide if that's valid or possible. And if it is, I set equal true, and I remove the clauses that have A in them, because these are satisfied now, and I keep repeating the process. If that turns out to be not good, like A equal true did not work, it will not create a solution, I do what? I set A equal with false. And if that also doesn't work, I'm going to output not possible. So you can say this is an n squared algorithm or so, not more than n squared. So why is this easy? Where's the fundamental difference between this and the 3SAT problem? This has enough structure to be solved. With the algorithm is just try A equal true, see what happens, see what happens. If it works, fine, done. If it doesn't work, try A equal false, see what happens, see what happens. If it works, done. If not possible. I mean, the algorithm is very straightforward. It's like with activities. You select the one that makes sense, the one that overlap with it, you remove because you can't schedule the ones overlapping, and you keep going, and that's it. What's the main difference between 2SAT and 3SAT? Where is that structure that works for 2SAT but fails for 3SAT? There's a critical point in this reasoning that I just explained here that just doesn't work for 3SAT. It works for 2SAT, but not for 3SAT. Can I do the same with 3SAT? Try A equal true, see if it works. If not, why not? Where it doesn't fail?
One value doesn't govern the value of the whole.
So if I say, in here I said, if I set A equal true, I'm done with all the clauses that have A in them, right? That would be true in 3SAT too, right? A equal true, every clause that has A in it is satisfied. What about clauses that have non-A? What happens in here with them? The other one must be true. What would happen in 3SAT, say, if I have non-A or C or B? If non-A is false, then what? C or B are true. That's the fork, because it's forking into two possibilities. I can't fork too much. Forking means exponential, right? If I multiply to 2 every time I move on, I'm going to end up with an exponential number of possibilities. This is not forking. It has enough structure to just keep going, pushing the inference, and solve it out. So there is a critical difference between 2SAT and 3SAT. That is, in 2SAT, I have enough structure to propagate my belief, my solution A equal true. But in 3SAT, this propagation rule means trying B or C. And every time I fork it in 2, if I move n times, that's 2 to the n possibilities now. That's not a proof that 3SAT cannot be solved. It's only a proof it cannot be solved this way. Now, again, we don't know for sure if there's no intelligent way to solve in 3SAT. That's still an open question, but most people, if not all people, believe it's not possible. So I expect you guys to know the fact that some problems are hard. They typically require a subset out of the input. And it's a question of whether they have enough structure to search for that subset or not. As an example, 2SAT definitely has that structure. Activities definitely have that structure. 3SAT doesn't have it. Knapsack doesn't have it. Subset sum doesn't have it. So trying a simple algorithm like this is guaranteed not to work. If you see such a problem in practice, I'm repeating myself now. Find me the best set of students that will make a good soccer team. Find me the best set of products on Amazon that together are covering your needs. Find me the best places to go ski in the winter out of subset of all the places in the world. Find me all the people that would be good recruits for some problem. Find me all the classrooms in a university that together as a set could satisfy all the exam requirements. All those things are asking for what? A subset out of a big item set. You should immediately pop the question, hey, is there an obvious structure to go by finding those things, like in the activities? If there is, okay, find that structure. You should expect an easy algorithm. Notice that activities and the 2SAT are very easy algorithms. They're not complicated. If you don't find such a structure, likely the problem requires brute force. Like try all classrooms and see which subset, try all sets of classrooms and see which subset. And that's going to be an inefficient solution. If you have 1,000 classrooms, you can't try all the subsets, right? Even with some elimination, say I remove the small ones, I remove the ones that have no heat, you still have to check a big subset of items, which means exponential. So what are other problems that work like this? So we're gonna call the class NP all these problems that are easy to verify the solution, like 3SAT. If somebody gives me a solution, I could verify it immediately, right? Same thing like with activities, or same thing with a knapsack. If somebody gives me a knapsack set of items, say install these ones, can I verify that that fits in the knapsack or not? Easy. So usually, we assume that a solution can be very easily verified, because if solution cannot be verified easily, that's clearly too hard of a problem. If I can't even verify the solution, what hope I have to find it? So NP is going to stand for solutions that can be verified easily, and P is going to stand for problems for which solution can be found easily. Now finding, it's much easier than verifying, right? That's the same like solving meter problems. If somebody gives you the idea of the solution, it's easy to figure out if it works. But if somebody doesn't give you anything, it's not so easy to find it. Right? So NP definitely contains more problems and harder problems than P. If we can find a solution in polynomial time, obviously we can also verify it in polynomial time. But the other way, like 3SAT, we can verify it in polynomial time. In fact, instantly, linearly, just check if the all conjunctions are satisfied. But we cannot find the solution in polynomial time. We need a brute force exponential time to do so. So P is included in P because every problem that can be found a solution in polynomial time could also be verified in polynomial time. Those are sets of problems. NP, sets of problems that can be verified easily, but not necessarily solved easily. P, the problems that can be solved easily also obviously can be verified very easily. So the question is, are those two sets the same? If 3SAT is solvable in polynomial time, which we believe it's not possible, but we don't know for sure, then they will be the same problem, right? 3SAT is clearly a problem in P because it can be verified. We don't know if it's in P or not. So we're not sure, is there any problem that is polynomially verifiable in NP, but not solvable in polynomial time? That's the big question that we're not sure about. We think there are problems there, like 3SAT, but nobody proved it yet. So there are many famous people who develop such problems, and some of them have to do with graphs and combinatorics. A lot of them have this flavor: find me a subset of things that has some property, and finding that subset, the only way how to do it properly is with a brute force solution. So let's look at some of these problems. We're gonna go through this. 3SAT is right here. There's some other problems in the book that explains theoretically how to go by. I think if you understand what I'm going to talk about today, it makes sense in a theory sense. If you want to, you don't need to study more in this direction, but if you want to do things like theory of computation and perhaps in a PhD program, you should go back to these other problems like circuit SAT and understand how they work. But they are too complicated to deal with them in half an hour. So we're going to start from 3SAT here. And this notion of reduction, complexity reduction, it's a very simple mechanism that says, let's look at the clique problem. Everybody knows the clique problem in a graph? No? Of course you do. You have a graph. What's a clique in a graph? Subset of vertices that have all edges in between. So clique of size 5 will be 5 vertices that have all 5 choose 2 edges. A clique of size 20 will be 20 vertices that have all 20 choose 2 edges. So the clique problem is find me in a graph the biggest clique. That is the biggest set of vertices that has all the edges in between them. Clearly I'm asking for a subset here, right? I'm out of the V vertices, find me a subset with the property that all edges are in between, and I can't, if I add another vertex to it, that's not a clique anymore because it's missing some edge. So that's one of these hard problems that we cannot solve efficiently. How do we prove something is hard? We applied this idea of complexity reduction. Here's how we're going to prove clique is hard. We're going to say, I know how to reduce clique. If I want to solve the clique problem, find the maximum clique in a graph. I'm going to say, suppose you know how to solve clique problem. Obviously, there is at least a solution to it that's brute force, trial possibilities. I'm going to show that a solution for clique problem effectively can also solve 3SAT. I'm going to kind of map the problem one into another, make a transformation from a 3SAT to clique, and say, if you can solve clique, because of that transformation, you can also solve 3SAT. But because 3SAT is hard, it's not possible for clique to be easy. If clique, if somebody maps, if we show a transformation that easily takes a 3SAT problem, and think about it as a subroutine calls clique and solves 3SAT, clique cannot be an easy problem, right? If clique can be solved in polynomial time or linear time, so 3SAT will be solved in linear time because 3SAT can be solved with clique. So that will be our complexity reduction mechanism. How we're going to show clique is hard? We're going to say, well, if it would be easy, 3SAT will be easy, and we think 3SAT is hard. Now again, we're not sure that any one of these problems, sure mathematically, it's actually hard. We believe all of them are hard, and we need to prove just one of them is hard, because see this dependency, if this is known to be hard, provable mathematically, because of the complexity reduction, all these problems also must be hard, because they all can be solved with 3 SAT. Problem is, the mathematicians, the very smart mathematicians of the world, cannot prove there's thousands of problems like this. And we can prove a single one of them to be that hard. We simply don't know, I've said this already, that any one of these problems cannot be solved efficiently. There is some speculation in mathematics that the reason we cannot prove such a thing, it's axiomatic. We just don't have enough axioms in mathematics to form our thinking. I don't know. So our job here will not be to prove that 3 SAT is very hard. Let's take that for granted. 3 SAT is a very hard problem. Let's say because many people try to solve it and nobody succeeded yet. Or because bank encryptions are still alive, nobody stole your money, right? But how do we prove that click is hard if we assume 3 SAT is hard? In other words, we're going to construct a mechanism here to solve the click problems using 3 SAT, or to solve 3 SAT using click. And that mechanism is going to be simple and say, look, click cannot be hard because if that, it cannot be easy, because if that's easy, 3 SAT will be also easy. So here's how we do that. Click problem. Click means find me a maximum click in the graph. In this graph here, this is a click of size 3. This is a click of size 4. Is there any click of size 5? No. So what is the maximum click in here? 4. So the key problem says, given an undirected graph, general, no conditions, what is the maximum click? That is a subset of vertices that are all connected. Seems like an easy problem, right? I mean, how hard can it be, right? That's the kind of problem that we can easily ask in a homework or so. If you are naive, you've never seen this before, you get the problem that's in a homework, find me maximum click, and you start writing a program to do so, right? That program never going to finish, or it's going to give an incorrect answer. You should be aware when somebody says find me a subset on items, immediately before you do anything, think about, whoa, wait a minute, this might be hard, and then you need to do some research. Maybe that problem is solved, or maybe you try to do a reduction or something. If it's a hard problem like the click, then you don't want to start writing an algorithm trying to solve it in polynomial time, especially if you know your graph is big. Like if you have a small graph, brute force might be working, right? How many subsets are there? 2 to the n. Suppose n is 10 vertices, 2 to the n is 1024. I can try all subsets, but if you have a big graph, so you are now Twitter or Facebook, there's no way for you to try to implement a brute force algorithm in a graph that scales the number of vertices to, you say, 1 million. Not even Facebook. It's a small graph, it's not going to work. So what we want to do here is to show that click is hard. How are we going to do that? By contradiction, we're going to say, let's assume click is easy. And we're going to show that if you know how to solve click, you can also solve 3 SAT, which makes click not easy if you think 3 SAT is hard, right? If click would be easy and you can immediately solve 3 SAT with click, then 3 SAT will be easy. But we think 3 SAT is hard. So here's how that goes. I start to 3 SAT, and I want to map the input of 3 SAT to click. So typically those reductions involve a very creative mechanism to do the reduction, like the one in here. 3 SAT comes with what? Clauses, right? Clauses with logical literals. For example, one clause will be not x1 or x2 or x3. Another clause will be x1 or not x2 or not x3. Another clause might be x1 or x2 or x3, and I may have other clauses, right? So how do I create a click problem? I have to create a what? I have to create a graph and then say, give me the click, the maximum click in that graph. Here's the graph that I'm going to create. I write this nice clauses, right? And I create edges between what and what. I don't put any edges between the vertices in the same clause, right? See, inside the clause there are no edges. Sorry, I said vertices, edges. And then I put edges from this to all the other literals in the other clauses, so I have edges to this and to this, but except some. Why don't I put an edge between those two? That's not x1 and x1. That's the only edge I don't put. So there's two types of edges I don't put. One is between the same clause, and the other edge I don't put is between a non-x1 and x1. That's the same between not x2 and x2 and so on and so forth. So now I have a graph. And I'm going to say, give me the maximum click. I say the maximum click is a solution to three-sat problem. That's the part that in complexity reductions, you have to come up with a creative way to do the mapping from one problem to the other. But then we also have to show that a solution for click actually corresponds to a solution for three-sat. That may require some back mapping, like some reverse mapping. So if the maximum click is here, that has a size, right? If the maximum click in here is 3, aka the number of clauses, I say that's a solution for three-sat. Let's think about that for a second, right? A clique looks like what? A clique looks like a bunch of vertices that have what? All edges on. Do we understand that? A clique must have all edges. That's what the cliques look like. There's a bunch of nodes, all edges in between. So suppose the maximum click that comes out here, what happened here? I took a three-sat input, that's a bunch of clauses. I constructed a graph. For this graph, I call the click subroutine that says, I'm going to return to you the maximum click. Now I say that solution immediately tells me if three-sat is satisfiable or not. Here's why. The click I need to satisfy three-sat will be of what size? 3, the number of clauses. If the click comes to less than 3, less than number of clauses, I say there is no solution to three-sat. But if it comes to 3, to the number of clauses, if the clauses happen to be 3 here, but suppose the clauses are 10 clauses here, right? 1, 2, 3, 4, 5, 6, each one with 3 literals. If the click comes of size 10, that click must satisfy the three-sat. Why? First of all, the click cannot have more than one node in each clause. Why is that? Because they're not connecting, right? So if a click comes to the size the same as the clauses, I have 10 clauses, the click comes of size 10, it must have exactly one vertex in every clause. It can't have 2 vertices in a clause because there's no edge between them, that wouldn't be a click. And it has 10 vertices, like 10 clauses, there must be 1 per clause. So now suppose the click comes x3, non-x2, and x3 here, right? That's the click I get in the graph. Why I can make all those literals true? The click comes to 1 vertex in each clause, right? And I say, all you have to do to get the three-sat satisfied assignment, make true, true, true. Now, obviously, that will satisfy every clause, right? Because every time there is a true in a clause, that satisfies the clause. But why is this assignment certainly possible? True and true and true. What would be the case where I cannot do such an assignment?
X3 and
If I have a x3 and not x3, that wouldn't, I can't make both of them true, right? But why is that not going to happen? There are no edges between x3 and not x3. So if the click return one vertex per clause, I know that no x1 would not x1 or x2 would not x2. So I can make all those vertices in the click true, and I have a true now in every single clause, which means I satisfy all the clauses. How many people with me? Okay. So let's have some questions then. What happened here? I assume 3-SAT is a very hard problem. Cannot be solved efficiently, right? Again, we don't have a proof for that. We just think it's a hard problem. But with that assumption, what I'm proving here is that click also must be a hard problem. How do I prove that? It's called complexity reduction. I'm going to map a 3-SAT instance, any instance, into a click instance, meaning I have to take those literals, logical, variable clauses, whatever 3-SAT has, and create a what? Click doesn't take Boolean variables. Click takes a edges and graph, right? Takes a graph. So I'm going to create a graph. So here's how I'm creating. I'm writing the clauses this way. I'm putting all the edges not inside the clause and not between x3 and not x3, or x2 and not x2. Now I feed this graph to the click. Presumably he's saying, hey, I can solve click very easily for you. Fine, take this graph, give me the answer. If the answer comes less than the number of clauses, I say, not possible to satisfy 3-SAT. If the answer comes the number of clauses, I say, okay, take that click, make all the vertices in the click equal true. That's possible because there is no A non-A in there, and it's one per clause, so then I just satisfy 3-SAT. That means if he has this procedure to solve click easily, like polynomial time or quadratic or linear, I could solve 3-SAT easily. I just create this graph, feed it to him, get the answer, boom, I have a solution. Right? But if 3-SAT is hard, click must be also hard. Otherwise, I just find a solution to do 3-SAT easily. That also assumes the solution is really three parts, right? Let's think about this solution. First is transforming 3-SAT into a graph. That's mapping the input to the input. Then is calling some procedure that says I can solve that problem quickly. And then once I have a solution, create back the solution of 3-SAT, right? So there's three parts. Click itself is a subroutine solving the click problem. But how is the transformation? How fast can I create that graph? Take an input to 3-SAT, a bunch of clauses with literals, Boolean literals, create a graph. Is that an easy thing to do or a hard thing to do? That's easy, right? This graph is very easy to create. There's nothing exponential in it. And then if somebody produces the solution for click, how easy is to create the solution for 3-SAT? Easy or hard? Easy. So I need to make sure the transformations are easy so that if the solution of click, which is the middle part, it's easy, then the whole thing is easy. Right? The solution of 3-SAT is effectively three things here. Map it to click, solve the click problem, take the solution, map it back to 3-SAT. If the mappings are easy, the only thing that makes 3-SAT hard must be what? Is solving click. So that's my proof that if 3-SAT is hard, click also must be hard. How many people with me? Now, I really need you to understand the idea. You won't remember this transformation. Next time when you hear about them, like, oh man, he said that just before the exam, and I couldn't remember what he said. That's fine. Any book you look for complexity reduction, you're going to remember it right away. You have to remember the nature of these problems. They ask you for a search space that's exponential. Find me a subset means an exponential search. And there is not enough structures to find it. So you have to look for some mechanism like this to say, my problem that you just give me, if my problem would be easy, that will solve some very hard problems, and then that's not possible, right, to solve hard problems that way, which means the problem I just got must be hard too. Let's look at another example. Vertex calculus. I want the subset of vertices so that it incident in every single edge. So I want the minimum subset of vertices in the graph such that every edge stays with either one of the legs. Every edge has two legs, right? U and V. I want every edge to be with at least one leg in that subset I'm picking. Again, what am I doing here? I want a subset of these vertices, which is minimum, such that any edge you pick, you have to touch that subset. You can't pick an edge that avoids the subset. Can anybody try to guess here what's the minimum subset of vertices so that every edge is incident in it? Incident meaning either U or V is in that set. What's the minimum? Pick few vertices here such that every edge cannot avoid that set. C,
A,
A,
H,
H. Is that enough?
E.
C, A, H. Is that enough to
And
incident all the edges?
F.
There's some edges that are not touching those three vertices. Okay, so what else do I need?
F.
F.
K, I.
I still don't have anything in Kij. Right? Do I have something?
Use J instead of H.
So this is maybe not max, and that's the minimum. I need the minimum subset. Anybody tries to do a minimum subset?
C A J
C, A, J, is that good enough?
and F.
C, A, J,
And F.
and F. How about IH? C, A, J, F. How about the H, IH? Is that touching it or not? So I want the minimum. For him, it doesn't work because HIH is not connecting to anything in here, right? Anybody else?
PIF.
What?
PIF.
E,
DE. For dog.
B, D,
I.
F, like that?
Yeah.
Is that good? D, I, F?
K, H is not K or H is not
K and H are connected.
K, H?
Then try one of them.
That problem, huh?
C A I G.
What?
Maybe like this.
C, A, I, G? I, G. Is that good?
B and D.
EF is given.
Huh. Maybe we have a candidate for the final. No, that I don't have to say NP complete. I just say here's a graph, here's a simple problem. Graphs are definitely going to be in the final. 3 out of 5 problems will be graphs. And for example, things like network flow always happen. Every single year there was a network flow problem. I'm not saying there's going to be one tomorrow. Just historically speaking, every year there was a network flow problem. Okay. Let me see. How do I think about this problem? I'm gonna reduce click to it. Click I already showed on the previous slide, it's a hard problem. So I'm gonna say, this vertex cover problem that I just showed you cannot be easy. Because I can use it as a subroutine to solve the click problem. If this would be easy, click would be easy, but click is not easy, right? So it can't possibly be easy. So here's how I'm thinking to solve. Again, I need a reduction. I need, somebody gives me a click problem, I have to transform it into a vertex cover problem. The transformation one way, then solve the vertex cover, get the solution, and move it back. So here's what I'm going to do. Suppose I get a graph. That's not the same graph. When I transform it, I leave the same vertices, right? But what happens to the edges? What edges are in here?
It's a not present.
And what edges are not in here? This is called G prime or G complement. This is called a graph that has the same vertices and exactly the edges that are missing. So if this graph will be a clique, will have all the edges. This graph will have what? No edge at all. Okay, this transformation is easy, right? Because I can go through a graph, and for every edge that is there, I take it out, and for every edge that is not there, I put it in. Now suppose I say, solve the vertex cover here. What is what? Find me a subset of vertices, minimal, right? That does what? Touches all the edges, right? It's incident in all edges. I say the clique, the maximum clique on the other side is the vertices that are not in the vertex cover. So what's the vertex, minimum vertex cover here? Z and W, right? If that's the solution for the vertex cover, I go back and say the maximum clique in this graph was all vertices except those two. Why is it that this must be a clique? Meaning, if Z and W are a vertex cover, all edges between all nodes except Z and W, all these edges must be missing here, therefore present here. Why is that? If there be any edge in here that's not connected to Z or W, this wouldn't be a vertex cover. That edge will not touch Z and not touch W, but that's the definition of vertex cover. It has to touch all edges. So if I remove the vertex cover, Z and W, there can't be any edge remaining. The notion that Z and W is a vertex cover says all edges must touch either Z or W. So if I exclude those vertices, there can't be any edge between the other four vertices. That means all these edges are present in the other graph, the first graph, which means they form a clique because it's all edges between the other four nodes. Isn't that nice? Okay. I cannot describe how much the difference is between how easy it is to see these things and understand it, say, yeah, it makes sense to me, and how hard is it to get to a theory of computation class and get one of these problems in the exam and say, okay, come up with a reduction. You know, boom. Like, it requires a lot of creativity to come up with this stuff. Right. Of course, once you see it, it makes total sense. Again, what happened here? I have a clique problem. I reduce it to a vertex cover. I do the map. In mapping, it's linear, right? I just remove some edges at some other edges. Solve this vertex cover, assuming there is a solution to solve it. Get the maximum, the minimum vertex cover. And the complements of these vertices not in the vertex cover, the other one, that's the maximum clique. Also a very simple mapping back. So now, if the clique is a hard problem, let's say we knew that from the previous slide, vertex cover must also be a hard problem because mapping it's easy. If vertex cover the subroutine will be easy. The whole clique problem means mapping, solve it, map back, that will be easy. Not possible. That means vertex cover must be hard. Who's with me? Yes or no? How about the subset sum problem? This is a version of the ones you have in the exam. In the exam, you had split the set into a subset and a subset such that the sum is equal. The general problem is find a subset that sums to exactly t. The particular problem, the midterm, was when t was exactly half of the sum. But in general, how do I find a set that sums to t? This is a knapsack problem. By now, we all know it's a reduction to knapsack. Why is this hard? That's an exercise for you guys. I can reduce 3 sat to it. So I don't have time to go through these details. But effectively, I take a 3 sat problem. What's 3 sat? A bunch of literals, booleans with clauses, right? I construct this gigantic table. And then I call subset sum and say, can you sum this to a certain value? And I show that if subset sum can solve this problem efficiently, then I can take the answer back and create a three-sat solution. The description is here. It's not easy to get by. I think it will take about 2 hours to fully understand how this reduction works. But by now, you should know the idea of a reduction. Take a problem, map it into the input of the other problem. Let's assume subset sum can solve that somehow. Then how do we take the answer, map it back to three-sat as a solution? This is the reduction here, constructing a bunch of auxiliary variables, and they say, this sounds to what I need. That must be a solution for three-sat now. If you have time after the exam and the grades, this is some good exercise for you to verify and understand complexity reduction. Okay. So what we said is we don't know if NP problems, all those problems I described are NP problems because the solution to them can be verified very quickly. Right? If somebody gives you a vertex cover solution, how fast is to verify it? It's very easy. Somebody gives you a three-sat problem, verify it's very easy. Click problem, very easy. And all the other traveling salesmen, Hamiltonian cats, all those problems, easy to verify, but hard to find a solution. That implies a search in an exponential space. So we don't know which one of these possibilities are. Most people believe is this case. P, the problems we can solve, it's a very small set of problems. And there is NP, co-NPs, a bunch of other sets. If P is equal to NP, we might have something like this when all problems that are verifiable are also solvable in polynomial time. No one believed this. There were some arguments a few years ago, but now everybody believes we are in this set. So if you go to a complexity, either you do a PhD or you take a theory of complexity course, when you get to these problems, you start studying things like what are these co-NP, and there's some other sets here of problems. Those sets indicate complexity, right? P is the easiest problems, the ones that we can solve in polynomial time. But we believe there's quite a few problems, like the ones I showed you, that are definitely not solvable in polynomial time. Now, what do we do about these problems? So assuming we believe that they are not solvable in polynomial time, every once in a while, we hit one of these problems in practice. Finding a vertex cover or a clique is a quite practical thing, right? I mean, a lot of problems in geometry are solved by cliques. A lot of problems in coverage, like you are UPS and you try to put your where should I put my warehouses or my distribution points? It might be a vertex cover. But this is quite, you can imagine a lot of problems that have a practical aspect, which means every once in a while I need to solve those problems. And I know I can solve them. I'm not going to try to solve them for real, but I want to do an approximation if that makes sense. So, for the vertex cover, what did we say? We want what? A set of vertices that's incident on all edges. And we want the minimum set. What we're going to do is going to create indeed a set of vertices that's incident in all edges, but what do I say? What do I mean when I say I'm not going to solve it exact, I'm going to solve it approximatively? It's not minimal. I'm going to create a set that's decent. It's not big set. I'm not saying take all the vertices of the graph. Obviously, that's a vertex cover, all the vertices. I still want a small set, and I still want to be incident in all edges. That's the requirement. But maybe it's not exactly the minimum. But maybe it's close to the minimum. And if you are UPS, that might be good enough. You know, it's not the best arrangement of your stores, but it distributes the packages okay. Same thing with water distribution of routers. Nobody can tell you the router's placement in a building is optimal for Wi-Fi, but it's good enough. I didn't put too many routers, and everybody has Wi-Fi on their devices, right? This is how kind of stuff works in practice. I can't find the best thing, but it's good enough. So here's a very simple algorithm that does that. Every time I pick an edge, I look at an edge that's not incident to my set. I construct this set little by little. So I pick a set, an edge, and I say, if this set is not incident yet, that means neither A or E are in my set. Add both of them. So every time I find an edge that's not incident to my set of vertices, I'm going to add both ends to that set. Very simple algorithm, right? I keep going. I pick the first edge. Obviously, there's nothing in my set. Put both vertices in my set. Now, since I have those vertices, I can ignore now, delete all the edges incident in those, because they're already in my set. All the edges incident in those vertices are done. I pick another edge that's not incident in my set. What do? Add both vertices, remove all edges incident to them, keep going. Very simple algorithm. For example, if I do this A and I, now that I added A and I can remove all the edges incident to A and I, right? Because those are already incident to my set. A and I are in my set. So then I pick another edge that's not incident to A and I add what? All of them, so I can remove now all the edges incident in them. I pick another edge, say CB, right? Which means I remove the edges incident in C and D, and I pick another edge, and I remove those, right? Now I have no edges left, which means by construction, every edge was incident in something. Because if there will be an edge that's not incident in my set, that edge will still be in the graph, right? So I'm clearly satisfying the requirement. Problem is this set, A, I, H, J, B, C, and E, F, is not the minimum. So what is the minimum? This has how many vertices? 8. And the minimum has? 7. So it turns out I can easily prove that my set, which is not minimal, is not too bad. My set is certainly bigger than the minimum, but not bigger than twice the minimum. So if I have a graph with 1,000 vertices, and minimum happen to be 12 vertices, that's the optimum. This algorithm says, I'm going to find you a set that does what you want, incident in all edges, and it won't be bigger than 24. Isn't that a practical solution? I mean, in terms of how many stores do I need to build, yes, it's not optimal, I need to build more stores, but not a lot more stores. It's just double the minimum. So we know the approximation ratio, twice the size. It's not the minimum, but not bigger than twice the minimum. Set cover problem, very related problem. It's not, I don't want the set of vertices like before so that every edge is incident in it. In here, these are like, I don't know, towns or something, right? And the notion of an edge is that the towns are close together. And I have to place schools or hospitals so that every town has either a school or is adjacent to a school. This is within 10 miles or so. So I'm going to say place school so that everybody is within 10 miles of a school. So I need here, this is not a vertex cover. It's very similar. It's a set cover that says pick a bunch of vertices such that every vertex is either picked or has an edge to a picked vertex. So if I pick, for example, A, I don't need to pick D, B, E, H, and K because those are adjacent to A. So what's the minimum set that can be picked here? Anybody wants to try? Pick the minimum set such that of vertices, such that every vertex is either in the set or adjacent to one in the set. This is not the same problem as before. I, but his is smaller than yours. So I want the smallest. Is ICF correct? Is everybody in the set or adjacent to something in the set?
Yes.
ICF.
Yes.
That's the smallest tree. So this is easily to show, like with the reduction, that's an NP complete problem. Like you can solve it efficiently. But how about an algorithm that gives me a set with this property, everybody's in the set or adjacent to the set. However, not the minimum, just close to the minimum. What would be a good idea? What vertex would you pick?
That's the one with the maximum degree.
Maximum degree. So let's do that. Maximum degree. Which one is the first maximum degree? A, right? That means I don't need anyone in the circle because I pick A, it's a maximum degree. And then I pick, I guess I pick G here, although that's not correct. J and C. So now I have A, G, C, J. This is a set that has the property that everyone inside of the set or adjacent to the set, but it's not minimum. Minimum is 3, the set is 4. I can prove here that the proof is some theory papers. The approximation ratio, what's the ratio between the size of the set that I generated with the greedy method versus the minimum? The ratio is log V, worst case. So if this V is, say, 1024 nodes, log V is 10. So my solution might be 10 times bigger than the minimum in the worst case, but not worse than that. It's an approximation algorithm. It does what you want, but it doesn't find the minimum solution. How about clique approximation? Find an algorithm that finds a clique, a valid clique, meaning a subset of vertices such that all edges are in there, except it's not the maximum clique. That's not easy to do. There is no good approximation algorithm for that. Some complicated proofs that no matter how hard you try, can't find a good clique, a good approximation of a clique. How about three-sat approximation? So if I wanna, here's the notion I'm gonna approximate three-sat. I'm gonna come up with an assignment for those literals. However, I'm not gonna satisfy all the clauses. Three-sat says you have to satisfy all the clauses. I'm gonna satisfy a lot of them. Not all of them, a lot of them. The algorithm is trivial. Make a random assignment of the literals. Literally, take your literals A, B, C, D, E, F, G. Each one of them independently, assign it either true or false. What's going to happen with the clause in three-sat that looks A or not B or C? What is the probability that this clause is satisfied if independently this was 50-50 true or false, 50-50 true or false, 50-50 true or false? What's the chance that this clause is now 1? True. Or not 1? What's the chance it's 1? It's satisfied. So how the probability of false is what? These are independent assignments. It's probability that A is false times, right, because it's independent. Probability that B is true times the probability that C is false. That's the only way to get a false overall. And what's the chance of each one of these to have? 50-50. So the overall chance of being false is 1/8. So the chance of being true is 7/8. 7/8 is like 83%. Now there's an expectation rule that says if independently every clause is 7/8, the number of clauses satisfied is about 7/8 of the total. That's a very simple expectation rule because these are satisfied independently. So this random assignment on expectation will satisfy 83% of the clauses. That's quite a lot, right? So it's not bad. but it's not satisfying all of them. The approximation ratio will be 8 by 7. Instead of satisfying all of them, it's going to satisfy just 7/8. And that's in expectation. It doesn't mean for every single problem you get 7/8 clauses, but if you do it enough times, chances are you're going to get about 7/8 on average. So it's a different sense of approximation, but nevertheless very fast in practice, right? Just a random assignment will satisfy most clauses. It's also good because it prevents adversary. No matter how hard an adversary try to set up those clauses for me to make my life hard, random assignments, no matter how you set the clauses, will always give me 7-8% of satisfying it true, right? An adversary can work on these clauses, but because it's random, I have a 7-8 chance to get it true. I have one more. Here's how I'm thinking you can solve subset sum. The problem again is I have a bunch of numbers, and I'm asking for a subset of those numbers that sum to a given value t or z, like in the knapsack. How do I get such a subset that sums to t? Here's a very simple idea. This is a hard problem, one of these NP complete problems, but here's a simple idea. I start like in the knapsack with an order A1, A2 to N, and I keep track of the possible values I've seen so far as a partial sums. So when I see A1, what are the sums that first of all, if I see nothing, I see 0, right? If I see, before seeing A1, the partial sum is 0. Once I see A1, what are my partial sums? 0 or A1, right? Because I can either include A1 or not A1. Once I see A2, what are my partial sums? 0, A1, A2, and A1 plus A2. That's my partial sums. I keep track of these things. Now I say I add A3. What would be my partial sums possible? 0, A1, A2, A3, A1 plus A2, A2 plus A3, so on and so forth, up to all over. Right? By growing up this list of all possible sums that I see, if I can do that, it's very easy to check at the end if t is realizable. How? Just check if t is in this list or not. Right? But what's the problem? The list could be quite long, right? Because there are so many options to put things in and out that this list could grow exponentially. So why knapsack is very good at solving this problem? Remember in knapsack we have integer values? So the problem is some of these values will be repeating in knapsack, right? If I allow arbitrary real values, there is a chance that nothing gets repeated here. But if those are integers from 0 to the total sum of all numbers, the total sum, say it's 200. How many values can I possibly have in that list? 200 values, right? That's how knapsack gets efficient. Even though the list in theory can be exponential, in practice, if it's limited to some values like integers, the possible values in this list, it's only from 0 and 200, and knapsack literally solves for all values from 0 to 200 in that computation table. But in general, suppose if I have integers, the list won't grow that long, right? Every time I advance the list, I should check if the value is already there to not duplicate it. So how can we do this? We say for I equal 1 to n, get the partial list that we have so far, and we take all those values in those lists and add the current value, right? That's what happened here. How did I move from here to here? I take all these values, I put them here, and then take again all these values to which I added the last element. If I do that in integer space or in some discrete space, there is a good chance that those values will actually be repeating a lot, and then I don't grow the list that long. Even if they do repeat, so I have real values now, and by adding values, I get this really unlucky input where nothing gets repeated. What do? There is a way to now prune this list a little bit. Even though things don't get repeated, I may use a heuristic in there to say some values are not useful for me. For example, the ones that are bigger than the sum. They don't repeat it, I can truncate the list. And there's some other heuristics to do this. Even though this theoretically is exponential, like the simplex algorithm for linear programming, this is quite efficient in practice, because in practice, things are very likely to repeat. Even if they're not integers. People don't use really random numbers. They use numbers like blood pressure and temperature, and those are measured in discrete values. So they're likely to repeat. They're likely to go bigger. And this algorithm is extremely fast. I can implement it with some optimization very, very fast. In practice, this is a very good algorithm to solve subset sum, even though theoretically it's exponential. So what did I do today? I show you some problems that are very hard. We don't know how to solve them. And we can prove one is hard by using the fact that the other one is hard. We did this reduction. If that one was hard, this couldn't possibly be easy because I can solve that one before with this one, therefore it's not easy. And then once we have these classes, polynomially solvable problems and polynomially verifiable problems that we think they're not the same, we need to come up with some practical strategies to solve such problems. And for some of them, there is a reasonable strategy that says, okay, I'm going to solve the problem, but not optimally. For some other, like the click, there is no good strategy. So there's an entire field of study in theoretical computer science called approximation algorithms, which says what hard problems can be approximated well, and how do we approximate it, what ratios do we get. That's very practical. If you ever hit one of those problems in practice, you want to use an approximation algorithm, but make sure you alert your boss or your user or your customer, hey, I'm going to give you a solution. It's okay, but it's not optimal, just so you know. Because an optimal one is not possible to find for your size input. With that, I think we're done. You're going to have to see me one more time. Okay? Don't miss the exam tomorrow. I hope everyone had a good time in this class. I know it's not an easy class, and I know other sections are easier than this one. I do. And it doesn't please me personally to make it hard, but I think it's the right thing for you to study it hard. Because the world today is very competitive, and half of what you need to do to be there where you want to be is problem solving and thinking. I know you need Java skills and programming skills and web skills and all kinds of other things. Data skills, networking skills, security skills, absolutely. But thinking is not replaceable with anyone. People who can't think, they can't solve any problem. So the fundamental of computer science and doing stuff, it's a good thinking mechanism. That's the part of this class. Now, for those of you who want to do PhD or research or more oriented algorithmic jobs like machine learning or data science or network science, I think it makes a lot of sense to spend more time than this class on this. I know any professor can say that my subject is very important, spend more time on it. But you should really judge this for yourself. Is it really worth, after the class is done and the grades are done, to go through the book and do the problems that you didn't do? Or even take another book. There's a very good one called Kleinberg and Tardush or something like that. Book, very famous. How about those problems? There's forums with problems, interviews, a lot of them about algorithms, Does it make sense to do those things? Is that what you want? Now, I'm not saying it's good for everybody. If you want to be an app developer, for example, you really need to know, be very good at developing apps, but general computer science and especially data science, network science, will sooner or later require problem solving, something that you haven't seen, something that you have to relate to, things that we may not have done in the class. There's quite a few things in this book that we didn't do at all, computational geometry problems. And this is still a basic algorithms book. Like, people go towards PhD or towards theory, they're fancier algorithms than the ones we've done. Okay. Please complete the trace evaluations. We'll have the midterms, grades today, papers tomorrow, and the exam I think it's, did we say WVH 108?